Hello and welcome to another episode of AWS Show and Tell. Today it's all about how to build physical AI agents with natural language. So we're talking real world robots today, and we've got all the experts here to dive deep into what is what in the world of real world robotics. But first, we'll show you a little teaser of what we got in store today. We've got agentic frameworks powering physical machines, doing really interesting stuff. And for the next hour, this is if you're in the audience today, lucky you, you get to ask questions to these wonderful, brilliant folks that have been working on this super. Oh, that's a cute one. Super interesting technology, including that spider and including my favorite of the robots. Oh no, what's gonna happen? All right, that was pretty sick. No, don't jump. Don't do it. And it's a barrel roll. It's a barrel roll. We've got that and much more in tune for you all today in store. My name's Trevor Spires. I'm a solutions architect from AWS. Thankfully, you've got not just me on the stream today. You got a bunch of other awesome folks. Let's go around the horn. Tell them who you are. We're going to start with you, C2.
Hello, Trevor. Thank you so much for hosting us today. I'm Çağatay Çalı. I'm from Agentic AI organization of AWS, and I'm a research engineer. I usually say research agent about myself, but research engineer. Yeah.
Love it. Love it. Aaron, why don't you take us out next?
Yeah. Thank you, everybody, for joining today. Looking forward to talk about Edge and physical AI. We have some special guests from NVIDIA with us as well today. So
very special guests. Yes, usually it's just Amazonians on this here show, but we've got two NVIDIANs. Is that what you call yourself? Ali, Alex, tell them who you are.
Okay, I go first. Hi, I'm Ali Sharakni. I'm a developer relations manager at NVIDIA, focusing on the robotics ecosystem at AWS. My background is in computer vision, and looking forward to telling you all about what we offer.
And hi, I'm Alex. I'm a solutions architect at NVIDIA, and I work on Omniverse and robotics.
Wow, this is all very cool. Friends, thanks. There's been a lot of work that went into the show, and I just want to say thank you all for preparing. And if you're in the audience today, ask some questions along the way. My hope is by the end of the session, you'll have an understanding of how you can get started experimenting with this awesome technology. So I'm going to throw up our content and say, take us away.
Yeah, so we just did the intros. These are the folks who are with us today. So thank you again for joining. And what we're actually going to be covering today, the good stuff. So we will start with Ali and Alex will give us an overview of physical AI, all the different components from simulation to training models, deploying models at the edge, that sort of good stuff. C2, my colleague here, will take us through a demonstration that we've built. He has some hardware with him. We'll be showing a demonstration of various robots being hooked up to agentic AI as well on the edge. We'll talk about how it works, go through some of the code, and then we'll talk about Strands robots. So in AWS, we've built Strands Agents, an open source SDK, making it accessible and easy to build agentic AI. We'll talk about Strands robots, an experimental addition to that. And then finally, we'll talk about what is next, some ideas for you to take away and go and have fun with. So I'll pass it over to Ali to talk about physical AI.
Wow. Take us away, Ali.
Thanks, Aaron. Yeah, so let's start with just going through what physical AI is. Physical AI is the embodiment of AI in different objects and things. So physical AI is capable of ingesting sensory information, cameras, voice, physical sensors, etc., and text prompts, and generate tokens based on those and pass them through a foundation model that would then generate actions that would allow the robot to interact with the physical world. So you might be familiar with, the classical notion of robots like quadrupeds and humanoids, but robots can take different forms as well. They can, like factories can be robust and smart. Of course, we already have autonomous vehicles, which are indeed robots, and we can also have smartness at city level. So cities can be also robots in some sense. So it's actually estimated that physical AI is a $50 trillion economy, and basically we have 10 million factories, 200,000 warehouses, 1.5 billion cars and trucks, and commercial cameras already existing, and we also have, of course, billions of humanoid robots coming in the future. Right. So I hope that convinces you that we have entered the era of physical AI. So autonomous vehicles, robots, and smart factories, these embodiments have existed for decades, but something fundamental has changed. So we've moved from arrays of multiple spatialized models, each dedicated to a specific task, to single unified end-to-end models. So these models actually can ingest and map sensored information directly and generate real-world actions. So, for example, you can just order them to, or gently rather, ask them to pick boxes and put them in a blue cart, or move them to station number 9, etc., etc. So that's actually very, very significant, because it enables like the model to generalize and interact with new environments, new conditions, and new tasks. It also dramatically improves real-world latency by eliminating the bottleneck of multiple sequential models.
That's what stood out to me, by the way. Whenever I was watching the demos, is like, okay, you can ingest video or text or like images into like a multimodal LLM and power, like it just, like you said it perfectly. Like you can now, like with this concept, you can now generalize across so many tasks and concepts, or at least there's the potential for that. So super exciting. Those ones on the left look awful lot like an Amazon warehouse, don't they?
Yeah, you're gonna see some more of those. Yes. All right. So it's actually, this is in fact enabled by what we call the tree computer framework, and let me walk you through those. So the first one is the DGX computer, or data center computer, that is used to train those foundation models, like for example the P6 or P6e instances on AWS. Then the second computer is what we use for simulation and synthetic data generation, for example, using Omniverse and NVIDIA Cosmos. And so that's used crucially to test and validate models in simulation before deploying them to the real world. You can run thousands of scenarios, stress test the models, inject edge cases for free, and verify those behaviors. And also you can generate a lot of synthetic data for training those foundational models, or fine-tune them as well. So this is the safety net that we need to generate those models at scale. And then the third computer is the AGX computer. That's the computer at the edge, which lives in the real world and interacts with the real world on the robot, either in autonomous vehicles or any edge device. And that's where the optimized models go and get deployed. All right, but there is a significant data gap when it comes to physical AI. Unlike large language models trained on internet-scale data, robotic systems face a severe data scarcity problem. We need thousands of human demonstrations to train a single manipulation task, and that obviously is very expensive and does not scale. So to address that, we need to use synthetic data to generate random variations and diversify those demonstrations for that manipulation task. For example, using teleoperation, you can capture some of those using Apple Vision Pro, and then the advantage here is that you don't really need a physical robot. You can just, if you have a robot model, you can already generate demonstrations using teleoperation. And once you have a handful of these demonstrations, you can use NVIDIA GR00T Mimic to randomize that workspace and add variations and validate each of these against actual physics. And then you can bring those validated synthetic motions into Isaac Sim and apply massive randomization using Cosmos to varying material, texture, lighting, and scene composition. Everything you need to bridge that scene to real gap. So what's happening here is actually very simple. We're replacing the need to do real world data collection at massive scale, which is very hard and expensive, with computation. So you're just using the first two computers that I discussed earlier, the DGX on the cloud and the simulation computer, to replace that need for physical data collection. And that allows you to develop performant robots at scale with low risk. Right, so just to double click on the data part of it, you can think of the data as a pyramid, a data soup with 3 layers. At the top, you have the real world data, which is very high quality, but as I said, it's very hard to capture and does not scale. But it captures the actual physics and real world interactions very well, of course, and that's the gold standard. But then we have the synthetic data that is very easily scalable and much cheaper to generate, but is slightly lower quality than the real world and doesn't capture that physics perfectly. And it needs a lot of sensory information as well to be perfectly modeled as well. So that's why the domain randomization is critical for that synthetic data layer. And then you have the internet layer data, which is abundant and free, but it's for physical interaction is not very usable because, for example, a video of someone picking up an object doesn't really give you the tactile feedback or force dynamics or the contact mechanics that you need to train that robot. So the key insight here is that synthetic data does not actually replace the real data. You just it would amplify it and would add domain variation and randomization that is needed to train a robust robot model. So to generate training data for your robot, you can leverage the family of Cosmos Foundation models from NVIDIA that would help bridge that gap. So we have 3 models out already. The first one is Cosmos Predict, that allows you to generate up to 3 seconds of realistic video given an image and to kind of generate future scenarios. Or you can have Cosmos Transfer, which allows you to amplify the ground truth simulation and diversify the environment to do texture mapping or add lighting conditions and generate different weather conditions, etc. And then we have Cosmos Reason, which is a vision language model that understands physical interactions and can generate optimal responses to queries using human-like thinking. And these are all available on AWS, and my colleague Alex would share some resources regarding that as well. Right, so here's an example of data augmentation combining NVIDIA Omniverse and NVIDIA Cosmos. So Omniverse provides physically accurate simulation of the robot and the scene, the assets, and the trajectories using very accurate physics modeling. On top of that, you can apply Cosmos Transfer to transform those simulations into a wide variety of conditions and add different lighting conditions, surfaces, weather, and material to create a rich, diverse training data set. Right, so just skipping. So this is another way to create synthetic data, is to use what we call dreams, using a single image and a text prompt. For example, here on the left, we can see the single image, and the prompt is to pick up the object that you can use for drinking water. And then you can generate trajectories and robotics sort of interactions in a video based on Cosmos Predict, and also have manual labeled trajectories using Cosmos Reason on top of that. So that can be, it's a great way to augment your training data set for robotics applications. In fact, our research team has trained Groot N1.5 using these dreams, generated in only 36 hours, as opposed to what would have taken around 3 months to manually generate and label data. Right, so now let's take a look at the end-to-end pipeline for what seemed first approach for accelerated physical AI development. So we start with the data collection and processing, as I described, and bring in all your video, text, audio, and synthetic data. And then you need to train your foundation model or the perception model, which is at the top. So that's using Isaac Sim and replicators to generate synthetic data and then feed it into a pre-trained model, and fine-tuning it and optimizing it for deployment to the robot brain. But then that's not enough. That's just your perception model. You still need to teach the robot to interact with the unit, with the physical world once it has perceived it. And that's the bottom part, where you can bring your robot model and train the policies using that foundation model and synthetic data that you have in Isaac Lab. But that's a loop. So it's a virtuous cycle where you would feed the demonstrations that are generated using that trained robot model back into the VLM that would generate, again, a foundation model for the robot to interact with the world. And finally, you can test and validate all of that also in simulation without touching the real world at all. So that enables you to do a complete everything in simulation, and develop and train and refine a model in a very efficient way before touching the real world. That would reduce the risks quite substantially. Right, so talking about specific humanoid robots, you can use NVIDIA GR00T VLA, which is fine-tuned at scale on AWS, and this is an open, customizable, cross-embodiment model that is optimized to run on NVIDIA Jetson models. And it enables reasoning and understanding, supports both fast thinking and slow thinking. For slow thinking would be used for reasoning typically, whereas fast thinking would be for reactions and intuitions. Right, once you have created all your synthetic data and trained the model, and now it's time to deploy to the real world. And physical AI demands ultra-high performance edge computing and fleet management. For that, Jetson Tor is a great computer. And here are some examples of early customers who we have engaged with. So you have humanoid robotics, as I mentioned, that needs real sensor data processing and VLA modeling and fast inference. And we have visual agents that monitor let's say warehouse environments or whatever environment that you have CCTV cameras in, and you can interact with the video stream and ask questions and generate alerts. You have more medical robotics and instrumentation that needs real-time sensor processing and inference, or you have autonomous robots and machines both outdoor and indoors. For example, for agricultural applications, again, Jetson Tor is a great candidate for those applications. And then you have high-performance computing and inference that needs high-bandwidth signal processing, which is, again, powered by Tor. With that, I'm going to hand it over to Alex, who will give you a bit more details on Tor.
Hey, thanks, Ali. This is NVIDIA Jetson Tor. It acts as the robot brain as a part of the 3-computer model that Ali had mentioned earlier. So using Jetson Tor helps make sure that the edge devices have the power needed to inference with these awesome models. You can see the improvements we've made from the last generation here. And then the NVIDIA Jetson AGX Thor developer kit. It's quite an AI powerhouse under the hood. It's accelerated by a Blackwell GPU. It gives you unmatched performance and scalability in a compact, power-efficient form factor. So it contains a Jetson T5000 model, heatsink and fan, 1 terabyte NVMe SSD, Wi-Fi 6E module, and some rich I/O connectivity, so you can use it as a powerful desktop Linux computer for development, or even tether directly to your robot to test and validate your models. NVIDIA can support virtually every model through our fully programmable architecture. And because Thor is based on NVIDIA Blackwell, we can run all the latest models and frameworks that you see here. So I think we should start with data. Physical AI systems need mass amounts of data for training. You can run NVIDIA Cosmos World Foundation model on a fully managed DKS cluster to generate synthetic data. Second, you can move over to training. Once you have that data, you need to train those models at scale. So you can run NVIDIA Isaac Lab and fine-tune GR00T Open Foundation model on AWS, allowing you to orchestrate large multi-nodes and multi-GPU training. Third, you can move over to simulation. Before you deploy those trained policies in the real world, you validate them in your simulated environment. With a single click, you can deploy NVIDIA Isaac Sim on Amazon EC2, where you can simulate thousands of scenarios simultaneously. And then fourth, with that sim to real, transfer this is going to be the critical bridge to test if the trained policy works in a real world. AWS IoT Greengrass manages seamless deployment of cloud-trained policies to the edge devices. You can deploy, monitor, and continuously update entire robot fleets from the cloud. And then finally, you can work on that agentic orchestration. And as we are moving from specialized to a sort of generalist architecture, the physical agents need to adapt and make decisions in scenarios they've never seen before. NVIDIA NIM combined with Amazon Bedrock helps the agent to reason, plan, and act in a real-world scenario. And then here are some codes, QR codes for our blogs to learn about our work using Isaac Lab and Cosmos World Foundation model with AWS.
All right.
Pass it off.
No, I mean, that was incredible. I mean, in fact, I think, would you mind going back to that last slide where we had the 6 pillars here? Here we go. This is what, a lot of our audience are like AWS administrators, and I love being able to see the way you could like mapping. Like I think we're about to see some physical robots in a second, but kind of mentally mapping what is the back end that's orchestrating all of this is just like a really cool view into things. Caggedy and Aaron and C2, do either of you guys have things that are worth shouting out here while we're looking at the slide that has kind of like the overlay of both the technologies? Oh, wait. Okay, wait. Hold up. I don't know. What was that? C2, hold up. What was that? All right. So you have, okay, wait. Okay.
We have everything. So I'm just gonna show, like, here's the Thor and here's the Orion, and we have the arms ready. I don't want to spoil too much, but yeah.
Wow. Okay, that's incredible. I didn't know you had all of that hardware sitting beside of you. I knew you had the arm, but I didn't know you had one of those beasts. Yo, what is going on, Eric? Eric, finally, we got a nice question. What do y'all think about this one? Ali and Alex. How does performance compare to like DGX versus Jetson Thor?
It's definitely a good question. I think that you should keep in mind that the DGX has a significantly higher amount of power needed. So it's going to be running with 8 or so large GPUs, can be even more. And you're kind of looking to make sure that you're not, don't expect too much power out of something that only pulls 130 watts. But
so slightly different performance. Yeah,
definitely. It punches above its weight, but it still can't hold up to a full server.
I think one of the things we'll talk about a little bit as well is this edge cloud synergy that we see, right? Where, of course, you need the robot brain, you need the Jetson Thor, the AGX, that kind of thing. But as we saw on Alex's and Ali's slide just now, there are some things that are infeasible on the edge, right? You need that huge parallel compute capability, which is where some of the AWS services you saw come in for training, simulation, that kind of thing in particular.
Amazing. Well, we got some Ali and Alex fans in the chat, so thank you all for walking us through the stack. Certainly a lot I need to learn there. Aaron, I think you've got something for us here queued up, actually.
Yeah. So, well, I'll hand over to C2 actually. C2 has prepared a demo for us all, so we'll run through that and we'll talk about how it's built afterwards.
So before we start, we used multiple technologies here to explain the concepts better. We use NVIDIA GR00T 1.5. Yesterday, there's a new version released, 1.6.
Yes.
I'm excited to try.
Very good improvements in there.
And I'm excited about explaining how we are utilizing LeRobot from Hugging Face. We love their abstraction. We use all of their products. And we use Cloud 4.5 versions, like a Sonnet 4.5 here. And we combine everything in the Strands Agent today. So shall we?
Yes, and there's a nice QR code again. I think you'll find some of the links in video descriptions to some of the code that we're going to run through here as well. So it's on C2's GitHub at the moment. We'll be moving that over to the Strands Agents organization in due course. Anyway,
So
let me pass this across.
okay. In this scene, we have an ID on the right side, and that's a Kira ID. On the left side, I have a Tor name select bot. I'm saying that move orange and white arm to home position at the same time. This action happens by agent using a tool named pause tool. We find it useful to have an agent access to the device and control the servo motor that is attached to save and record poses. Home pose is the safest position for to start manipulation tasks. So between VLA, LLM can actually start moving the robots for us. So this is very useful than I imagined. Initially, I built this tool for going back to the home position, but it's became so useful, I wanted to share with the people. So on the left side, you can see when I send a message to our Slack, that forwards message to the edge device. In this case, Thor is handling the message and executing the post tool, and it's moving the both of the arms at the same time and sending me a Slack message back. Please note that this happens in the edge. It's not happening in the cloud. It's just running on the edge. It's connecting through the bedrock for the LLM inference, but this is using the edge device to execute everything on it. So we have one more video in the next slide, which is actually opening and closing grippers. To explain, we have a full control of the servo motors here, right? You can see I have an arm here with me. It has 6 servo motors on it. And every time I want to open and close a gripper, I can independently control these devices. This gives agent to opportunity actually ping the servo motors. Are they healthy? Are they working? If they are working perfectly, it's gonna be good for me. So in this video, it just opens and closes the grippers, but let's see the next slide. So in the next slide, I'm saying take a photo and explain what do you see. Context is the gold, because once you have context in your agents, they can act in physical world better. They can react things. They can trigger a vision language action model as we use GR00T today. So we are using language models photo taking action as a take photo tool. As you can see, it sends me over Slack, and I'm gonna be switching to myself in this video, I think. But yeah, so you can see that it explains to me, it sees me in the scene, and we will be using this camera feed for running VLAs. As Aldi and Alex mentioned a couple seconds ago, VLAs are using video streams, language actions, and robot state as inputs. So system 2, which is the VLM, takes the video input and language input, but diffusion head is actually moving the arm. So let's see how actually one VLA looks like in action. So
yeah, and one nice thing about what's being shown here as well is this is combining, the large reasoning power of a model like Claude 4.5 with an edge Jetson Thor with GR00T, all working together, right? Where the LLM at the front, Claude 4.5, could also be a local model. We've used Quen and some of those sort of models locally as well to orchestrate things. But it gives the robot the ability here to, for example, receive messages over Slack, write natural language messages and also send them back to us as well. Explain what it's seeing in the image, right? It talks about C2's fluffy gray jacket, for example, in the description here.
Before we move to the next slide, I want to say Nemotron is launched from NVIDIA and benchmarks are pretty good. I'm so excited to test it. For the edge device inference, it's amazing. So I'm just letting people know I'm being an NVIDIA fan here.
That's amazing. So could you help me like with one thing for the folks that are watching? What is the agent running locally on the so everything is happening, the code's executing, everything's on that agent, and except for there's an API call going into an LLM out in the cloud somewhere.
So I can lay down the idea for better picture. The runtime is actually here. So runtime is completely an edge device. And that device is connected the arms over USB port. So edge device is fully listening Slack events as Slack socket actions for the geek people, right? Like me. And whenever Slack sends us a message, we are processing on the edge device because there is no other way to make it faster to receive that request.
So we have a couple of examples of more sophisticated actions as well, right? You saw a couple of very simple actions, a home pose, open close gripper, take a picture, describe what you see. More sophisticated actions as well. So I'll let C2 describe those.
So in this case, we are using NVIDIA GR00T 1.5. We fine-tuned on Aaron Su's data set. I want to call out his demonstration here. It's picking up a banana and placing to the tray. It's picking up the orange, placing to the tray. This is trained, fine-tuned, they call post-tuned version of the GR00T. With 1.6, it's claimed to be way better to react to post-tune results, but I'm so excited to post-tune 1.6 right away after this call. But in this case, we are using agent and VLA. VLA is attached to the agent as a tool. In this case, we are using as an orange arm. For language model, it's a just orange arm with a language parameter attached. Language model says, okay, can you pick up the apple for me? Can you pick up the banana for me? Can you pick up the orange for me? And VLA is the one actually applying that to the real world. Interesting thing is, if you move the target away from the arm will follow. So that's the beautiful thing.
Like it reacts in real time.
Exactly.
Nice.
Exactly.
We have a couple more examples as well. Just jump through these.
So I think using VLAs are amazing, but there are deployed robots to the physical world already. And in this case, we see one Boston Dynamics spot is used by an agent. The action was, we need to change your battery. Can you flip over? And then it flips over so we can pull the batteries out. This action is programmed using the Boston Dynamics SDK. It's not a VLA applying these actions. We are using existing SDK of Boston Dynamics to make this happen. This is an addition to the VLAs. So we have a really cute spider here. It follows the people, dance as well. And this demonstration explains what kind of different robots actually might be used by an agent. And we just want to demonstrate more and more robotics applications in the real world.
I love the cute little wiggle that it does, the spider butt. Okay.
So how does it work, Aaron? Can you tell us?
Yes. So a few short demos there. Now we get to my favorite part, some code. So a few different components we've seen today. If we start with a very basic agent here, this is using the Strands Agents SDK. You can find out more about that at strandsagents.com. But we're creating an agent here, you can see on that second line, very simple. just creating an agent object. And towards the bottom where we invoke the agent, you see we're passing in a couple of messages here to its context. We're asking it a question, what objects do you see? And then we're passing it the bytes of an image. In this case, that image is a camera frame. Have an example function here that returns the current camera frame in bytes. And invoking the agent here is very similar to what we saw C2 show, right? Where the robot took a photo with the camera of C2 and explained what it saw in the scene. Very similar way to do this. And this essentially gives your agent the ability to see, right? You can think of it in that manner. Obviously, you have to use a model here that has support for vision as well, right? Images, that kind of thing. So in this example, we've used Claude 4.5. We've had a lot of success with Qwen 3 VL model, for example. There's a new Nova Omni model from Amazon as well. We've had some good success there. So a few lines of code here just to show how you can add vision information to your agent's context with Strands. You also have different kinds of sensory inputs, right? So could be the battery percentage, it could be a fuel level, right? For a remote vehicle, for example, or an autonomous vehicle. In this case, you can see we have this get battery level tool. Again, just simple interface, simple syntax. We really tried to keep it accessible and super simple developer experience here. So we write our get battery level function, pseudo function here, but you can see it's returning the battery level as a string, right? And because this is a tool, that string, with the battery level percentage, the minutes remaining, gets added to our agent's context when our agent uses this tool, and is then able to answer the question that we're posing here, how long until you need to recharge? It will be able to answer that from the current battery level. Again, super simple developer experience and interface with that one function, and the @tool decorator, it allows me to pass any Python function to my agent. Also TypeScript, which we just released 2 weeks ago. So we can add vision and sensors to our agent. Robotics are mostly three things when they're deployed, right? That we've seen here. It's sensing, reasoning, and acting in a loop. So it senses things like battery level, looks at the scene through its camera lenses, perhaps a video feed or a microphone input. It then reasons about them using a model, perhaps Groot or perhaps an LLM like Claude for larger scale reasoning. And then it acts, right? As we saw some movements, some pick and place actions. At the very beginning, we saw a humanoid robot moving a chair and jumping off a table. But that last piece is acting, right? So the Boston Dynamics example that C2 showed, here's some code that makes that work, right? Again, we have a very simple function, battery change pose. We're using the Strands Agents tool decorator, and this tool is using the Boston Dynamics SDK under the hood, right? So it has these prepared poses. It has like a sit command, a stand command. It's just calling those through tool use. Really useful when you're perhaps using robot hardware that comes with a pre-built SDK. Now we get into the good stuff. So we have sensors, we have a basic agent that can read various bits of information and sense and reason about them. We showed how you can do acting with an SDK, but not all robotics have an SDK, right? Maybe it's a robot we're building ourselves, or a custom piece of hardware, or maybe we're actually building a smart city, as Ali and Alex talked about, or maybe an autonomous vehicle, right? Or a medical device. So in some cases, we actually need to tune and deploy our own model, right? We can use NVIDIA's simulation and training products. We can do that on AWS at scale, deploy to our Jetson Thor on the edge, connect it all together with Strands. The VLA models here, the integration with Strands, again, a tool. We have this execute manipulation tool. Same thing as we just saw. I've done everyone the favor here of cutting out a few hundred lines of code in this function. It's a pseudo function. I wanted to show this to just explain the loop that's going on when we're using a VLA very quickly. So you'll see this while loop, while task is not complete. For every iteration that the task is not complete, we're doing three things. We're getting the observations, which means getting that camera image, getting the robot's current position, the state. Ali mentioned the tactile inputs, that kind of thing, getting all of that from the robot hardware. And then we're sending that to the VLA here. We have that VLA get action call, sending all those observations, the camera image, etc., to the VLA model. In this case, it's NVIDIA GR00T. And then finally, we get from the model the actions to apply, right? So from the robot's current position, given the language instruction of perhaps place the apple in the basket and the current camera feed that the robot can see its position, can see the apple, it will generate actions that move it to the apple, grasp it, pick it up, right? Move to the basket, place it, open the gripper. So it's that loop. The task complete thing here is interesting. It's very much an open research topic. These VLA models today don't exactly have a concept of the task being complete as such. You know, if you're familiar with building AI agents with LLMs, they often have like an end turn response, right? When they're finished, they emit that. These VLA models, it's open research topic. There's sequence VLA, SEQ VLA, which is a research paper that does implement this. Very, very interesting. And you can also implement this with things like VLMs, right? We could have maybe a Quen model or maybe even a NVIDIA Cosmos model running locally to actually analyze the scene and determine if the task is completed or not. So lots of code cut out of this example to actually make that work, but it just shows the example of the loop. So building this today is a lot of code. I'll hand over to Shagatai again to C2 to talk about how we've made this a lot simpler.
So the idea was how we can start programming with agents and VLAs, and I started working from backwards. I started using NVIDIA GR00T source code and try to learn how I can run the code, how I can actually train the models, and how I can actually apply these things to the real world. I find the code base really good, so I can start copying and pasting some samples. But since we are trying to make things simpler in Strands, we took one step ahead and we talked with NVIDIA, we talked with Hugging Face, and we asked from their feedback. If this interface looks good, are we doing something good here, or are we just doing something bad? And so far, we are getting great feedback. And idea behind this, can we make an abstraction on top of LeRobot's robot class so we can accept any open source robots with their cameras, with their LiDAR sensors, with their Bluetooth or whatever you are attaching to your robots, and connect that robot into a real device and actually run the device. So in this Strands Robot class, we have a simple interface, try to describe the robot. Today, we accept a couple parameters, start with tool name, which is visible to the agent. Agent will use the robot arm in this example. Robot type is SO101 follower, which is an open source 3D printable arm you can buy online or 3D print at home if you have an opportunity, and attach 6 servo motors on it. In this example, I have 2 cameras. One of them is on rest, you can see here, and one of them is external. I have here. So in this case, I'm using a dual cam data config since I'm using 2 cameras. So after I define these variables, I need to define which port I am attaching the robot to the edge device, which is shown as dev TTY ACM0 here. So once you define this configuration and attach that variable into your agent as a tool, that becomes a ready tool for your agent. Agent can trigger your tool in sync way. That means agent gonna invoke the tool, wait until n number of seconds, and then stop. Or it can trigger an async way. It's gonna start moving the arm until I say stop. These are the two ways to invoke this robot implementation. Please note that this is under experimentation stage. Once we feel more comfortable, it's going to be part of Strands organization for all of us. Can we move to the next slide?
Yes. Yeah, it shows. So on the previous slides, I mentioned I cut out a few hundred lines of code. I did not do that here. Like, this is actually the full code in this case, right? With this, you have an agentic robot that uses Claude 4.5 for reasoning from Amazon Bedrock. You can also use local models, right, as we mentioned. And it's connecting to this robot arm, right? And I can now just send natural language commands like fold the pile of laundry, and it will do that for me. So this is the full interface here from the Strands robots class.
You know, we got a question from the chat I was going to save till the end, but since somebody asked, I need to throw it up on the screen. Is like, if somebody wants to get started doing their own robots, is there any sort of like kit that you all recommend for somebody who's just wants to get their feet wet on a budget, a hobbyist like a guy like me who wants to have something for the home lab?
To be honest, I bought all of the NVIDIA stuff. I have Orin Nano Super at home. It's running every day. I have Orin 64 gigabytes here, and I have Thor, which I love the Thor most. But I would suggest, if the scale is small, you can buy any of these devices you love within your budget. In addition to that, you might buy standard open arms to experiment robotics at home, which I believe that's the cheapest way. Please correct me if I'm wrong, Ali or Alex. And yeah.
Yeah, there's the NVIDIA Jetson series, really, really good. And also, yeah, as you mentioned, right, C2, some of the open source 3D printable hardware, right, robots basically, that Hugging Face support, right, like the SO101 arm that you have there, the little spider that we showed on screen. There are mini humanoid robots as well that Hugging Face have just launched, the Ricci Mini.
Yeah,
those are really good for getting started as well.
Or if you want to splash a bit more, you can use a Unitary robot as well.
Yeah, a lot of scale, right? From the more 3D printable home kind of robots, right, all the way up to, you know, scaling up to like humanoid robots of varying degrees, to like autonomous vehicles, right? So to smart cities. So take your pick on that scale.
So I hope this answers the question, Trevor.
I think you answered it quite well. You gave folks a lot of options that they can explore and kind of pick what's right for their budget, if they're ready to jump in the deep end and get some local GPUs or a little open arm and some somewhere they can run the agent.
One nice thing as well that Tito and I have been doing when experimenting, right, that Ali mentioned, if you don't want to splash out on the hardware immediately, you can run all of this in AWS, right, and have the pay-as-you-go model, right, where you just pay per hour for the EC2 instance kind of thing. Obviously, you're dealing with network overhead and latency, but if you're running this in a simulator, for example, and not in the real world with an actual robot just yet, you can do all of that in the cloud as well. So many options.
There you
Before
go.
Talk about what is next, I want to explain the architecture slightly. Okay, I'm just going down. So the Strands robot uses a small architecture by design. The full code base is around 2,000 line of code, but abstractions are in the place today to actually talk about. Strands making the tool orchestration and planning. It triggers a VLA, which is a GR00T today. We will support other VLA providers too. That VLA can run on edge or on cloud, which Aaron just mentioned. We are using LeRobot's robot class to make the robots are actually get the observation and send the action back to apply. And this is the loop of actually applying the VLA to the real life. So robot hardware gives a state feedback to the policy, which is VLA, and agent also receives the status updates of the execution. Strands robots comes with a couple additional tools with it, which helps to start a GR00T inference on edge, gives you some camera inputs, gives you the serial context. You can start a teleoperation and calibrate the robots you bought. So thanks so much for time. Yeah.
Okay. So what is next? I think you have some ideas here as well, C2.
So I think the next step for us, bringing the simulation, NVIDIA have Isaac Sim and Isaac Lab, and using them within our orchestration strategy, so we can actually make the simulation generate data for us and train the models with it. And bringing more VLA providers to the scene, Hugging Face have an async in inference and implementation we would love to introduce into our code base, and more like a sim to real. But I want to give NVIDIA team to explain what is next from their side, to be honest.
Yeah, I think as well, I'll let Ali and Alex jump in just after. There's this very like open research area as well, I would say. These World Foundation models, the VLA models, their capabilities are growing really, really quickly. If you look at the comparison of GR00T 1.6 to 1.5, just a few months apart, 1.6 is much more capable. Made me very, very happy to see that. So kudos to the NVIDIA team there. I think there's a lot of interesting ways that this stuff will go. There have been papers from Google, for example, and DeepMind, where they are at inference time changing model weights, right? So it's kind of like a form of memory for the model as it's doing things, kind of remembers what it just did, right? With the weights of the model actually changing at inference time. So instead of pre-training everything into this static state and deploying that, you're actually able to deploy something that can, in essence, learn over time through experience as well. I think we'll start to see a lot more of that. And it goes to Ali's point about the data pyramid, where we're currently lacking a lot of data on physical movements and that kind of thing to train these models on. Simulation helps a lot there, but also deploying these kind of technologies in the field and having them learn through experience, right, is also another avenue that's, I think is quite exciting as well. I don't know, Ali, if Alex, you have thoughts on what's next for physical AI?
Yeah, no, I think that's great points you guys made, and I think in addition to the blogs that we've shared, of course, I highly recommend you checking out build.nvidia.com. You see the full catalog of the models that we have deployed, and all of them are available also on AWS, on EC2, and some of them are going to Bedrock, as well as EKS, etc. So it's very easy to deploy them on AWS. Nemotron models are fully open source, including all the architecture and the training data as well, and they include VLMs, and they're all available on Bedrock serverless as well. Great for large language model or VLMs or maybe incorporating into your physical AI applications. And as we discussed, I think starting in simulation is definitely the right place to get your get started, and it's cheap and scalable, and you can train a full model and test it and before going to prototyping and deploying in the real world. So
yeah, I think with Groot, I don't remember the exact time, but Chagatai and we have a model duck that we've been training pick and place kind of stuff with. I think we trained Groot in just a few hours. Yeah, there's the duck. I think we trained Groot in just a few hours on an AWS instance, right? And if you're using the P6s, the P5s, it's far shorter, for a single training run.
Casual. Oh, just casually flexing that he can get his hands on a P6. Good for you, Aaron. Good for you. Yeah, you got friends. You got friends. Hey, we got some cool questions coming in the chat that I definitely want to address. One comment that, as an AWS SA and fan of all of our conferences, I gotta make is, Dan has a pretty cool suggestion here of integrating this into Deep Racer. I'm sure today the traditional ML method of Deep Racer is probably a little bit more task specific, but it would be really interesting to see over time what some like as this develops, if there's some kind of like real time movement
maybe you
through
could
an
have
AI model,
maybe you could have like Deep Racer but autonomous driving style, where it has like a, I don't know, mini city to drive around or something.
Yeah. Oh yeah, that's a really interesting way to do it. Yeah, see how you can like prompt it to get through it without
we can have these models like Groot and other things driving it around for us, maybe. So I just wrote a note down for that. So yeah, good point.
And one more question came in other than the hardware. Like I'm not smart enough to ask this question, but I just saw the Strands SDK. Were there other libraries, SDKs being used behind the scenes there to orchestrate what was going on?
Yeah, Chagatai.
For the Boston Dynamics Spot robot, we are using Boston Dynamics SDK, Spot SDK on GitHub. For VLA actions on the arms, we are not using anything else than the Groot Infinite.
Yeah, the Spot example there, it was using the Boston Dynamics Spot SDK in the tool that we added, pretty much. That was it, really. And these tools can call anything, right? It could be any SDK. Or with the VLA approach, we skip all of that and go lower level, where we're directly calling the model and directly applying the actions to the hardware. So
I live in Boston, and so and my wife actually works at a AWS NVIDIA partner called Mass Robotics, does a lot of events in the area. But funnily enough, I can't get enough of the dogs. I see the dogs everywhere because they're celebrities in Boston, and it never gets old watching them do their little dances. It just never gets. It's always magical. It's always magical. Gentlemen, it has been an amazing hour, super action packed. Really can't say thanks enough for bringing the energy and bringing the information. I think folks are really gonna, those folks that were here live, thanks for chilling, and those folks that are watching this on the recording, hopefully this inspires you to go get yourself a kit, start digging into this stuff. Or if you're already a builder in the robotic space, hopefully this gets you aligned with kind of like where things are headed in the future. So just wanted to say thanks again for everyone. We'll be back same time, same place. If you're a fan of this show, in fact, we're going to be out for a couple of weeks, but we will see you in the new year. And I hope everybody enjoys their holidays. All right. Take care, and we'll see you all in a few weeks.